everyone, and welcome to our keynote session, Containers and Kubernetes, another step forward for Synergy applications. My name is Rachel, and I'm joined by our presenter, Kelsey Hightower. Kelsey had the privilege of recording his session during the hottest day on record in Sacramento, 117 degrees. So he really got a feel for Sacramento then. Just a little bit about Kelsey. He is a principal engineer and an author of a book we will be raffling later on called Kubernetes Up and Running. He started his career by opening a small consulting shop 20 years ago, and since then has progressed through the halls of Google, Puppet Labs, New Relic, and Core OS. He describes himself as a system administrator by trade and a programmer by necessity, but a problem solver at heart. And later in the presentation, Kelsey will be joined by our CTO, Jeff Green, to dig deeper into this topic. And as in all of our sessions, there will be time for Q&A after the presentation with an opportunity to use mic if that is working. In the meantime, you guys can feel free throughout the conversation if you want to just post some questions in the Q&A chat area. So without further ado, I am going to start the video.
Hey, I'm Kelsey Hightower, and if you're looking to understand how to make use of this existing software in this cloud-native world, then you're in the right place. We're going to start right here at the landing page. I'm pretty sure a lot of you, unlike myself, are really familiar with Synergex and all of their products. You'll notice one thing on their website. Your digital transformation starts here. Now, normally when I see this, I tend to freak out because most people can't tell me how they're going to get from point A to point B. But what we're going to talk about in terms of digital transformation today is taking the Synergex software that you may know. I'm new to this space. And just to give a lot of people who are also new like me a little preview of what we're talking about, on my way here, I'm actually live in Sacramento, recording this in front of the team. And one thing I noticed that when I was renting my car, I took a peek around the counter and I saw their screen. And you would notice that in 2022, there are a lot of people that are still using the equivalent of green screens. Like, yeah, look at this. This is stuff that's like straight from the 80s, the same decade I was born. This is the software that's pretty much still running the world. If you're booking airline tickets, checking into a hotel, maybe even a rental car, these are the type of user interfaces that people are still using. Now, I'm pretty sure what you're thinking is maybe people should just rewrite this into web frameworks, pick something like JavaScript or maybe even mobile apps. But look, let's be honest. This stuff is super fast. It does the job well, and it's been doing the job well for decades. And so the question we want to ask today is, how do we take this software, the software that has been tuned, works for the purpose, and try to leverage new environments like the cloud, cloud-native technologies like Docker and containers. I'm pretty sure a lot of those things are new to a few people here. So I want to make sure that we walk through. So our goal is to take this software. It's been running for decades. Powers a lot of the world that we live in today, and see if we can leverage some of those technologies. Now, what technologies am I actually talking about? Well, I come from the CNCF world, the cloud native computing world, and a lot of you will get a glimpse at something like this. This is the CNCF native computing landscape. There are tons of tiles here, things from logging, compute services, there's even databases here. And what has happened over the last couple of decades, we've learned a lot on how to run these systems, how to automate them, and give them fancy interfaces to run our applications and the services that we're building. But the challenge is how do you go from where you are, running software like we just seen, to leveraging this stuff? Well, the first stop for most people will be something like Docker. But one thing I need you to understand is, number one, you probably already understand 80% of the things that we're going to walk through today. So what I'm going to try to do is take the classic software that we saw, we're not going to say legacy, we're going to call it classic, and we're going to figure out, does it make sense to even leverage any of these new platforms and services? Now, before we start jumping into tools like Docker, there's going to be another important tool called Kubernetes that we'll also dive into, but we have to understand the starting point. And for most people, that's the existing software that you're already running, And the thing I like to do is to consult the documentation. Now, what you'll see here is all the steps necessary to run some of these products and services. And these are very detailed. Why? Because we need to make sure we have the right environment, server requirements, and then of course, using this documentation, you can write your own automation scripts to automate the deployment of that software. And we've been doing that for a long time. Like if you're a system administrator like me, this is the typical thing that you do. You learn the software well, maybe you run through it a few times manually, and then you write some automation tools. And automation is great, but what happens when we want new abstractions, right? So automation is taking documentation like this, maybe a virtual machine, writing a shell script, and then having a go at it. And look, it works. Don't get me wrong, but I think we can do a little bit better. It's 2022. So what if we could take that same software, all of these instructions, and package things up? And this is where Docker comes in, right? So what you're looking at here is a Docker, website. And so the thing we need to understand is what is actually happening under the hood. And so I just want you to think about one fundamental idea. We need to take that documentation and turn it into a set of instructions that this Docker tool can use to package up the application. So I'm just going to pop over to my terminal. I'm going to have a look at one of these, what we call Docker files. All right, so I'm going to just list my directory. And what we're going to do is we're just going to pull open one of these Docker files. Now, get it, there's a lot of stuff going on here. So I'm going to step you through it nice and slow. Now, first, the Synergy software is pretty big. I have no idea on how to build it. And remember we talked about digital transformation? Well, look, it's never going to happen if your partner or vendor doesn't help you out. And luckily for me, the Synergy team has done exactly that. They've already containerized many of the things that I need in order to leverage containers for my existing software. The other things that are down here are all the things I talked about before. You're going to have to automate some of the installation components. For example, to get this software working, we're going to have to install a few third-party dependencies, some security components, some .NET components, and there's a lot of things here. But at the end of the day, the pattern that I want you to understand, if you know how to automate software being installed on a VM, then you know pretty much everything you need to use something like Docker to do it. Instead of running those bash scripts on servers, we're just going to throw the script inside of this Docker file. That's the one big takeaway I want you to have here. So we're going to take existing skills and just convert it to a new packaging tool. So what do we end up with if we did that? Well, the cool thing is, once we build these applications, we can now store them into a container registry. Now, some of you may have never seen one of these, but think of these as like normal package registries. I've used many Linux distributions over the years, and a lot of times those packages are stored there. If you want to think about like one of the most primitive packages we all know, if you came up around the time I did, software used to come on CDs, and I'm pretty sure some of you have a big book of CDs laying around. Well, you can think about that as your repository. Each software package has its own CD distribution, and typically, back then, you didn't guarantee access to the internet, so you put everything on one of those CD-ROMs so that it could be self-contained. You put the CD in the drive, and ideally, you can install the entire software by just using the CD alone. Containers are very similar to that. The goal with the containers are to say, hey, what if I were able to create a self-contained image of all the software? Now, what I'm going to be installing today is the RCC software. I'm not going to pretend I'm an expert here, but it's one of the most popular software packages people use for these reservation systems. And in this case, with the help of the Synergy team, I was able to create 3 different container images, one for the RCC engine, the client, and the API. Now, with all 3 of these container images in place, I don't actually need to understand how to build all of this software, including all the .NET and operating system dependencies. This is great. This is what we mean by new abstractions. So instead of handing me documentation and shell scripts to automate the build, just give me software packages that are ready to go. And this streamlines things big time for me. Now, what do you do once you have these container images, these Docker images? Well, this comes the next step. Remember all this documentation we talked about earlier. This has instructions on where to place those applications, how to configure those applications. You even have things like storage requirements. There's a lot there. And again, the imperative way of doing this, again, logging in and typing a bunch of commands on a virtual machine, or running that bash script if you've done it a few times before. But we want to actually transition to another one of those components from the cloud native landscape. Now this one is tricky. I think we all understand how to package software and ship it around. We've been doing that for a while. But the next component that I'm going to talk about in the cloud native world, well, this is the one that tends to throw people off the most. And this one's called Kubernetes. Now, it has a very strange name. If you want to know what Kubernetes means, it means helmsman. So the person who's in charge of driving or steering the ship. And the idea here is that we can take those Docker images and deploy them to the machines that we have in our environment. Now, I'm going to let you in on a little secret here. When we talk about Kubernetes, most people think about this as some big, magical container runtime. And we usually talk about it in terms of cluster, like one big thing. But I'm going to let you in on a little secret. If I were to look at the details of my cluster, under the hood, what you will find is a bunch of virtual machines. That's right. This cloud native, new fancy technology is backed by virtual machines from 2 decades ago. The thing that's different here is the fact that we're going to introduce orchestration. So think about it. If you don't understand what orchestration is when it comes to things like container images or things like schedulers that automate the placement of your workloads, then you might be the scheduler. And what I mean by that, when I was a system administrator, we would take all of these VMs and ask yourself, how do you decide what applications run on what VMs? I'm going to give you a quick reminder. We had 3 of those images, the API, the engine, and the client. I have 3 machines here. Should I put them all on one? Should I split them across all 3? Well, that decision making, that's actually the act of scheduling. And how do most people manage this stuff today? I'm going to show you. Don't be ashamed when you see it. What most people do is they break out the handy dandy multi-user database. Spreadsheet, that's right. People usually take the inventory of VMs or bare metal machines, they just throw them in a spreadsheet. And then they use this to try to keep track of what software is installed where. I'm going to try to use another analogy to try to bring this home a little bit more. Now, one thing I want to explain is the difference between automation and scheduling or active management of your workloads. So I'm going to try to do that by playing a game, Tetris. All right, I'm going to double click on Tetris here. And if you don't know about Tetris, this game is older than some of the software that I was talking about a little earlier. But it still stands the test of time of explaining how scheduling works. So the first thing I'm going to do is try to explain how automation works. So think about Tetris as an analogy for software, right? Software comes in different shapes and sizes. And the goal is when we write our automation tools, well, we try to write a script that will take our software and just put it in the right place. I don't know about you, but most bash scripts aren't that sophisticated. Typically, it's one click, automate the deployment. If there's failures, then most scripts don't account for that. I'm going to show you what that looks like in practice. So the first thing we're going to do here is start the game. I'm going to show you one-click deployment, the thing that everyone brags about if you go to the fancy conference. One button, and then you let the script do its thing. Notice to the left and right that I'm not actually even playing the game correctly because I'm not using any of the information that comes in real time to make any decisions. And this is what automation looks like. It's just this idea of saying, I'm trying to predict the future and my script will run under those conditions and only those conditions. They don't tend to react to anything new. Now, let's talk about introducing something like Kubernetes into the mix. Now, Kubernetes has a different job. Its goal is to slow down. And remember, part of the analogy here is we don't have unlimited compute. We only have so much CPU and memory and disk space to go around, so we have to be very careful on how we place our workloads. So let's look at what happens when Kubernetes attempts to automate things. One thing it's going to do is look at each workload individually and try to make a decision on where it should run. So in this case, I'm trying to find the best node inside of my cluster to run my actual application. Now, if you look at the way I'm doing this here is I'm placing each workload in a way that consumes the right resources. Sometimes we call this the best fit. And we keep doing this over and over again. But here's the interesting thing. Notice this piece that's coming in. This could be a machine learning job or a batch job, and it only needs to run temporarily. So I move it into space, and once it drops down into this well here, the nice thing about Kubernetes, it's going to clear up and free up all that memory and disk space for the next workload. You can see here, I can move this piece around, and Kubernetes will make the same type of scheduling decisions that I just did here. That's the difference between automation and orchestration. One takes account of real-time information, kind of this constant feedback loop on where things should be and where things are, so it makes the most optimal scheduling decision. And again, 80% of this stuff is the stuff that you're doing already. It's just Kubernetes represents this checkpoint in 2022 where we've gotten this stuff to production and we have slightly better tools for doing it. So hopefully the Tetris analogy helps you understand why something like Kubernetes is important. Now you would think, hey, Kelsey, look, this software is on its last leg. And people have been saying this probably for decades. We're just going to rewrite it. You're probably not. Why? Because it totally works. And so that means is we shouldn't abandon this software. We should just find a new home. Even software like this could benefit from the ability to be containerized, packaged in a consistent way, and then also leveraging things like cloud technologies in order to run them. So even though the data centers in which these things are running are going away over time, it doesn't mean that this software has to go away with it. This software will probably outlive your current environment. For many people, this software has already outlived the original server that it ran on, and that's the power of software. The thing is, what we need to do is transform the way we manage this software onto these new stacks. And so that gets me back to the original thing we talked about. Your transformation starts here. And so first, we packaged our software and we ended up with nice container images, so that's repeatable. And now we have access to a system like Kubernetes, so we can automate things. But there's one step missing. How do we tell Kubernetes what to do? Remember, I said bash scripts are out in this world. We need to do something more declarative. And remember, the knowledge that you already have plays an important role here, because even that will be used to create what I'm going to show you next. And these are what we call the Kubernetes manifest. So we have the knowledge, we have the container images, we have a cluster that's backed by a bunch of VMs, but we're not going to target the VMs directly. We have a much better tool of doing that. We're just going to call the Kubernetes API and let it decide where to put those containers. So the next thing we need to do is actually articulate to Kubernetes what we want it to do. So I'm going to close out of this Docker file. Now here's the next big step. And I get it, it's going to be a bit challenging because you've never seen it before. But here's the thing. Given that we have all the other baseline stuff, and of course the most important ingredient to this entire equation, well, that's you, right? You're still the most knowledgeable person in this particular setting. We need to describe to Kubernetes exactly what we want to have happen. Well, there's a few things. I need all three of those containers, and they actually need to share storage with each other. Now, with the help of the Synergy team, they taught me all about it. And so what I was able to do is to transcribe all of that knowledge into this Kubernetes manifest. Now let's walk through it. We're going to take our time because this is the part of being declarative. We actually need to tell the system what we want it to do. So let's take a look at what we're looking at. The first thing is I need a place to store my data. And I know if you've heard things about containers back in the past, you may have heard things like they're ephemeral. When you restart a container, all the data's gone. Well, the truth is, all software works that way. If you restart most software, most of its data usually is stored in memory, and if you want it to stick around for a while, well, you need to store it onto a disk or a database, back that up. So the first thing we're going to start with is a type called persistent volume. Now, an interesting thing about this, I'm just creating a standard persistent disk for my cloud provider. In this case, it's Google Cloud. This could have easily been Amazon's AWS or Microsoft Azure, and honestly, even your own data center can support these things. So even though we've been talking about cloud native stuff all this time, this type of thing actually works in your own data center. And the reason why we call it cloud native, we're talking about the practices, the techniques of managing software, not where it runs. And so it still makes sense to leverage this even in your existing data center. The next thing we have here is that we want this volume to be mounted later with this file system. And we have a storage driver. This could have easily been something like NetApp or whatever your cloud provider uses. Here I'm identifying how much storage I actually have. And I'm also going to do something around how often it should be read and written to. Now this part is super important. If I was dealing with NFS, then we can have multiple writers. But this is actually a physical block device that's going to be mounted to the server. We got to be careful here. This is more of a traditional file system, like the kind you find on a standard operating system. This doesn't support reading and writing from multiple containers or multiple VMs mounting at the same time. Now I could do some interesting things like mount it to one VM, so the application I'm going to deploy can read and write to it, and maybe mount it to other VMs so it can be read-only. But you need to be very careful with this. What this does is tell Kubernetes exactly how to handle that volume. And again, this volume, this data block device that I have for storing things long-term, it doesn't actually live inside of Kubernetes. There's a little controller that will take this definition and actually configure whatever API I'm using, the cloud provider or something on-prem. Let's move on to the next part. The next part is where we actually define our application. Now, there are many ways to define apps. If I was writing a basic static or website, this file would be much simpler. I would actually use a different type of object called a deployment. But the software we're defining, software we're going to deploy, it's actually going to be stateful. It's going to actually use that volume, and depending on where Kubernetes puts it on any three of those machines, it's going to have to mount that volume and make sure that it's injected in the right container. So in that case, we're going to use what we call a stateful set. Don't worry, there's a ton of documentation that explains each of these fields. I won't go through them all right now, but just know the goal here is to declare what you would like Kubernetes to do. Notice, I don't even pick any of the machines. We let the control plane do that for us. I want one copy of this stack. I'm just going to give it a name called RCC. And the goal with this is that all of those container images that I showed you earlier, if you look here, I have the client, I have some environment variables, and turns out a lot of this stuff just actually runs over SSH. Still a proper protocol today, and it's actually used inside the software. So I'm just informing the system that this particular container will be exposing port 22. Remember that volume that I talked about earlier? I'm also going to tell it where to mount it for this particular container. Now, if this sounds a little confusing, think about spinning up a VM, attaching a disk to it, and then running these same applications on the VM. You still have to mount that disk to some data path. That's all I'm doing here. I'm just being declarative about it, so that way Kubernetes can take the best steps necessary to make it happen. But remember, there's three applications. So we also need to do the same thing for the engine, right? This is the core logic for one of those programs that we saw earlier. It has a ton of environment variables. Where do I get these from? Ideally, you're going to get this stuff from the documentation. So wherever it advises you do it here. And we also have the API. There's a lot of boilerplate down here, but the other part that I want you to see is that we have to expose some of this stuff either to the outside world or inside of our private network. That's going to be up to you on what's best. In this case, I want to expose port 22 so we can bring up one of those green screens. Going to remind you what that looks like. So if you ever want to bring up one of these, typically it's going to come over port 22 and it would just show up on your display. Now, the other thing is there's an API. So the good news is if you're going to be automating this stuff through maybe a different piece of software, then you can actually have an API port open as well. So that's what I'm doing here. I'm just pointing to the various ports inside of this stateful set. All right. And then we're just doing the same thing for the individual services in case I want to have different network paths here. All right, so this is the declarative state. Remember, you have those container images, reproducible software, and we have our declaration. So what does this all result to? Now, the good thing about this is, if I were to go to any Kubernetes cluster anywhere, ideally, I only have to run one command, assuming that that data volume is set up, and if there's any data that you need is populated in that data volume, then I should be able to run one command and have this application stack come up. So I'm going to show that to you now. So if I look in this directory, we see that Docker file that we reviewed earlier, that was used as a foundation for creating those 3 other images. What we got now is that declaration, rcc.yaml. And so what we're going to do now is call kubectl apply-f. I'm just going to give it this file. And what's going to happen is it steps through each of those declarations and pushes them up to Kubernetes. Behind the scenes, there's a bunch of control loops that are parsing those configs, setting up the data volume, pulling those container images, placing them on the right machines that have enough memory, CPU, and the ability to mount that disk volume, just like the game of Tetris we were playing earlier. If everything is working, we can actually list the results of that deployment. You can see here I started a little early so we can actually have things move a little faster. But basically that one command is declarative, so that's why nothing broke when I ran it again. This is super important. This allows us to check in these declarative configs and move into a world normally called GitOps. Instead of running a bunch of scripts from our machines or a jump box, we can actually check in these declarative configs and then ship them in the proper release window. The cool thing about this, it works for software that was written recently, aka modern software. And just how we just demonstrated just now, it works for existing software, like the one we saw earlier. How do we prove that it's working? The next thing people are worried about is this a black box? When this stuff is running on a VM or bare metal machine, look, I get it. You know what to do. But in this new environment, it feels like you have to start all over again. Well, remember, most of this stuff is the same. For example, let's say I want to see the logs from all 3 of those things. What I can do here is say kubectl logs, and there's also an API. I'm just using the command line tool to make it streamlined a little bit. So kubectl logs, I'm just going to give it this pod name, and think about the pod kind of like a VM. It holds 1 or more containers and any volumes that it needs. The next thing I'm going to do is do the particular container. So let's look at the API really quickly. So if I call the API, this is going inside of the container and pulling the logs that are being written to standard out. Now, the Synergy team did a really good job of packaging up this software so it can actually run in a container-friendly environment. Even though I'm showing off Kubernetes here, this could have easily been a VM or bare metal machine running the Docker runtime to support these containers. That's the beauty thing about this. You can get portability once you go this route. And so we can do this for all of them. I can do this for the engine. You can see what the engine is actually putting out. You can see here that it's giving me this FBI warning. So if you don't have a license for your Synergy software, you might want to get right with them before they come after you. And then we have one more piece of software, which is the client. Now, you may be thinking, all right, Kelsey, that's the logs, but what if I need to actually debug a little deeper, right? Sometimes you just really need to be inside of the environment where the container is running, meaning you need access to disk space, you need to run additional commands. I get it, I've been there. So in that case, we can call kubectl exec, and what we can do is get a terminal, an interactive terminal, and we can actually log into the machine. Now this isn't quite SSH. This is actually authenticating using my local credentials. Matter of fact, every command we were running here was using my local credentials to execute commands against the cluster. So in this scenario, what we want to do is get a shell inside of one of those running containers. Let's just pick the client, for example. So if I click on the client, we got to give it a command. We'll say we want a bash shell. So we'll say bin bash. And depending on how the container is built, you may or may not have a shell in there for this to work. So what's happening under the hood here is the container images that I got from the Synergy team, they have all the right things in it. All right, so at this point, you can see that I'm actually inside of this container. What does that mean? Well, I can run normal commands. You can see ls. You can see all the files that are available that have been written either by that container image. Remember that volume that I talked about earlier? Well, that's also here. That RCC data directory has all the things that I specified earlier. And these are the files, the original database, maybe some licensing files, the whole nine, and a bit of configuration. Well, that's mounted in the right place on that container. Remember I talked about when you restart the containers that you can lose all your data? Well, what's happening here is we're mounting in a volume so that doesn't happen. So no matter what machine Kubernetes picks to run this particular workload, that data volume is always going to be attached just before the container starts and injected so it's always in the same file system mount that it's looking for earlier. This is what gives you that virtualization or VM feel that you were doing before. And so as you can see here, it doesn't have to be a black box. Even commands like the ps command work. So we'll run ps-aux, and you can see all of the things running in this deployment. There's a licensing server, there's the software itself, and there's that SSH daemon so I can actually connect to it to get to one of those screens. Now, pretty sure a lot of you out there know more about the software than I do, but if you were to connect to it, ideally you'll see something like this. So what did we learn today? We learned that just because software was written a long time ago doesn't mean it can't take advantage of some of these new techniques. There's a lot of stuff in the CNCF landscape. Look, it's massive. But for most people, you only need a couple of items. Things like Docker give you consistent packaging mechanisms, and then Kubernetes is your orchestrator and it allows you to declare your deployments. It turns all of this documentation into a simple YAML file where you can declare and describe the state of the world, and therefore all of that knowledge, all of that skills of how to automate systems gets captured or serialized into a repeatable set of patterns. I'm pretty sure you all have a lot more questions, and to help me answer some of them, I'm going to introduce Jeff Green to the stage. Welcome, Jeff.
Well, hi, I'm Jeff Green, Synergex CTO, and you already know Kelsey. So my sort of first line of questioning that I think matters to our users is this, so I saw cloud native computing. Is this exclusively for people who are in the cloud, or can you do this really yourself? Can you set up all this infrastructure in your own data center? Can you do a little of column A, a little of column B? What are your options?
Yeah, so I would say, one thing I try to emphasize in the demo was everything I was showing was layered on top of the virtual machines. So whether you're running VMware in your data center or a bunch of Raspberry Pis somewhere in the closet, more than likely you're going to be able to install a distribution of Kubernetes on top. And the goal there is that you get this API. That command line tool that I was running? The goal is that whatever you have, so if it's on-prem, you probably have something like Cisco switches, NetApp for storage, and VMware. If you're in the cloud, you're going to use their IaaS platform or their Kubernetes service. And even companies like VMware now have their own Kubernetes service. So I think where we're at now in 2022, it's an open source project, Kubernetes and Docker, and they're designed to run anywhere where compute runs, and then it just becomes about integrations. So cloud has their own set of integrations like block devices and APIs for mounting and detaching from storage. But look, you can get that from OpenStack. You can get that from VMware. So I think the answer to the question is you should be able to run this anywhere where you can run some VMs and install or get a distribution from Kubernetes.
All right. And if I'm in a production kind of environment with this, is there a way for me to basically deploy a test version before I deploy the actual production version and switch it on for users? Can I do that blue-green kind of deployment model here?
Yes, I want to make sure people kind of understand, like in your own data center, let's say you're running similar software to I was running now, like the RCC server. Let's say you just got it all on one VM. Let's just keep things super simple. Get everything on one VM, and you got your block device there. So now let's ask a question. If I wanted to deploy a new version and give it to a subset of my customers, or maybe even all of my customers, it's up to you to decide, think about what you would have to do. If you're using a local disk, that's going to be hard to pull off on a different machine. And so this is where you start to ask yourself, like, where does the data live? And so I think the first question you're going to have to ask, and I'm going to just talk about this from a VM bare metal perspective first, because the solution that I describe here will also be the solution that you use in Kubernetes land. So if I had two VMs and I want to have a new version side by side, well, of course, obviously I could just deploy the new version on the same VM and have them both up at the same time, and maybe they're listening on different ports. And then I can hit them on different ports using the existing data volume, and hopefully the software can deal with two application stacks hitting the same data volume. If we were to stretch it to a second machine, then we have some challenges, mainly around how do I get this data volume accessible to this other machine? And this is where other file systems come in. I think we talked earlier about things like Luster's distributed file system that will give you a block device that can span more than one machine. That's one solution, so that solves your data problem. Then of course, if you have two VMs in the mix, then you're going to need like a load balancer to tell traffic where to go. Does it go to the existing version or does it go to the new version, assuming both versions have access to the distributed file system? That pattern I just talked about, Kubernetes can replicate that same pattern. So instead of like I did in my demo where I'm using a block device, instead I would just move to LusterFS, right? Set that up. And then what that should do is give me access to a set of file systems across multiple instances in my cluster. Okay, great. So now our data is distributed. We have this fancy thing that's replicating that data across all the machines. All right, just like in the VM world, check mark. Second thing would be, I would have to create another stateful set. So the first one could be called, blue-green is a very common pattern when we think about this. So the existing version 1.00 might be blue, and then green might be 2.00. Okay, so this is blue-green. And so what I would do then in that scenario is I would create another data stateful set, one called green and one called blue. And then they would both have different versions, so that way I can deploy them at the same time. And then Kubernetes can schedule them wherever they want. And then wherever they land, they will have access to this distributed file system. And I'm making an assumption here that the software can deal with locking between...
It does locking just fine.
Perfect. So as long as the software is doing that, then the last challenge will be is how do we send traffic to the right version of the software? So if you're running SSH to the green deployment 1.0.0, then there's probably going to be some IP address that you're using to do that. What I would then have to do is tell some customers, here is your new IP address, because each of those stateful sets will have their own IPs. That's a nice thing that Kubernetes gives you. And so it's going to come down to configuring the consumers of that software to use the right IP address. And that's how you would basically do blue-green deployments using something like Kubernetes.
Can you just have the load balancer sitting in front of those two and switch it in the load balancer side?
You can. It's a very common pattern that people do today, where depending on the load balancer, right? So for L7 load balancers, this is fairly straightforward. Each of those backends, like I know the RCC API, great, put both of them back there. And then you can configure the load balancer to say if people come in from a particular IP address or region of the world or some header that you've given, like a customer ID, then you can send them to any version of the backend. Honestly, the load balancer just treats them as equal backends. It doesn't even know what versions they are. But it's up to you to decide by saying, I have multiple buckets of backend. So if I think about an average load balancer, you can group your instances into different buckets, right? Like targets, right? So anything that comes in on a particular path / version 1 goes here. Anything that has a particular IP, or you might just decide, I like 10% of my traffic to go to the new version. That's all handled at the load balancer layer. But once you have two stateful sets deployed, you're going to have two different IP addresses. It's up to you and your load balancer to group them as two separate targets, and then configure your networking layer to just send the traffic, and Kubernetes is none the wiser.
Okay. Are there any performance downsides? Is there any significant overhead to running in this environment instead of just being one big VM?
Well, it depends. So in my demo, I actually took all the components and put them in one pod. So they actually live together. So they all have the same shared lifecycle. The API, the engine, and the client all come up together. and that disk volume was attached all to one VM. And I think the common confusing point is containers just like virtualization, right? Like if I have a bare metal server, we know that there's overhead of putting a hypervisor on top and then carving that bare metal machine up into smaller virtual machines. There's been some optimizations, like there's faster ways to access the local storage. But yes, there's going to be a bit of overhead to run in a hypervisor environment. That's just how virtualization works. But containers are a bit different. Even though we say containers like this is a whole new computing abstraction, it's not really as big of a jump that virtualization is. That's a huge jump. This is about actually having one kernel isolate processes at a deeper level. So you're still running under the same kernel on the same machine. And that thing is basically taking your containers and splitting them off into their own what we call namespaces. So you can only see these mount points. You get your own IP address. It depends on how you deploy things. Once you start deploying things across multiple servers, then you're back in the same performance overhead with networks in between each component. But that would also be true with like virtual machines or bare metal. So when it comes to just pure containerization, I take this container of some software that was running on a VM before, and now running on a VM through containers, performance should be roughly the same because you're not virtualizing anything. You're not emulating any hardware at this additional layer. So you're just using this to get a packaging step. You get a runtime that takes that packaging, extracts all the bits, almost like that CD-ROM example that I gave. You just want everything to be self-contained. So it's just using like the old school chroot. It's just taking that entire container image, exploding it out, and making sure that all your dependencies are co-located together. Guess what? You're not running in another virtual machine. You're still using the same kernel that's already on the machine itself.
So it's just a really efficient way to package all of those things together and run them isolated.
Yeah, and the isolation part, we should probably explain that piece a little bit. You know, if you just took a VM and you just installed all your processes as root, well, they would probably have access to all the file systems. They would share the network. So if two things wanted to bind to like port 22, that wouldn't work. So what happens is now modern kernels, I mean, when I say modern, like 15 years ago, we gave the kernel the ability, and some people would say even 30 years ago, if you think about AIX, right? These things have always had the ability at the OS level to create this logical container. And so that logical container says, I can now give you your own namespace, your own limited view of the world. So when I run this process, I can hide it somewhat from the other processes. So instead of this seeing all the file systems and all the paths, I can give it a limited view and in some ways kind of lie to it. You can only see the paths that I've chosen to give you. And you also get your own IP address. Don't worry about it. If you want to bind to port 22, that's totally fine. I'll let this other pod or container bind to port 22 as well because you have separate IP addresses. So you get all the flexibility of like a VM and separation containers and isolation, but you get the conveniences of like a modern operating system where everything's just running on the shared kernel. Last thing I'll say here, you got to be careful. If you want true isolation, you're probably better off, even under Kubernetes, making sure your workloads run on different machines. You can do that. I didn't show you, but in that descriptor, I can put what we call anti-affinity policies. Maybe one service has data that you don't want the other one to ever access, even under a bug in the kernel. There's been what we call container breakouts. That's when there's a problem within this kernel that allows someone to escape their isolation. And now I can see more file systems than I should. That could be a problem. So to guard against that, we take our containers and we tell the scheduler, don't run these side by side. Matter of fact, prefer a different machine and just don't run it if you can't find one. And so that anti-affinity policy allows us to get machine level isolation.
All right. And in your experience, what sort of, when someone goes down the Kubernetes path, what's the biggest avoidable mistake that people come in and run into?
I think the biggest mistake is looking for Kubernetes best practices and starting there, right? It says best practices on the doc, and a lot of people think that's the way they should learn it. I think the best way to go about it is to figure out what's right for your software. So if you told me that RCC prefers things like Lustre when it's going to run across multiple machines, then just run Lustre inside of your Kubernetes environment. In many ways, what you want to do is take the things that you know well and serialize it into the Kubernetes manifest and tell Kubernetes just to do that. Now, once you have something powerful like Kubernetes, for example, if a machine were to go away in a Kubernetes cluster, then Kubernetes is going to be smart enough to move that process to another machine. This is great. But unfortunately, a lot of people don't have software that can deal with that. And so what does that mean? Making sure your software doesn't have to start in a certain order. Making sure your software doesn't depend on one machine having all the data local, right? You need to think about replication. Either you could do it in the application stack, or you can use something like Lustre that we talked about earlier that will replicate the data for you. These are architectural decisions that you can leverage to get even more out of Kubernetes. So think about it from a layer perspective. To me, don't fight two battles. You're already moving from a world you know to one you don't. And I recommend most people get started by taking software that they already understand how to maintain, manage, and deploy, and even upgrade, moving that into containers and Kubernetes, getting some value, because you can get a lot of value just from doing that. But then look for other opportunities like health checks, metrics, monitoring.
All right. Well, that sounds pretty good. So I guess in closing, I would like to say for any of the other stewards of these very long-term product sets like ours, that there comes a time, because we have these platforms and we have to look out for the people that are on them, that you have to start looking at what's coming up and containerization and making sure that your software works in those containerized environments, and that you can basically tell people, don't go over there, go over here. You'll be successful if you go in this direction, in ways that are specific to your software stack. So for us, that was mostly around how do you deal with data storage and licensing. But for others, they may have other problems. But someone's got to tackle that, and it's best if the people that are working inside the platform can tackle it, because outside of the platform, you're dealing with too many unknowns at the same time, and it's not going to work out.
Yeah, I would say one last thing here is that also you all know how to make the changes, right? So if there's any problems, you all can actually take the delta and fix it, right? There's a saying, it's easy to predict the future when you're working on it. And so for people to adopt these futuristic platforms, they'll need people like you all to make it happen.
All right. Well, thank you, Kelsey.